welcome to this new course on under nature and properties of materials. This is the second part of that course. You can call it second module on phase equilibria, and so this is, let me write the title, it's phase so this is basically under nature and part 2. Okay, so this course is useful for students who don't have a undergraduate degree in materials or metallurgical engineering or ceramics engineering. It's for students who want to work in materials or who want to have knowledge of materials, but are from different backgrounds such as mechanical engineering, civil engineering, chemical engineering, or even MSc physics, BSc physics, chemistry. So all the different backgrounds who don't have exposure to phase formation, the concept of phases or phase equilibria in materials, they will find it useful. And also the second year or second year undergraduates or master's students in material science and engineering who have not had exposure to such a course earlier, they will find it useful. So let me first begin with the contents that we will study in this course. So we will begin with introductory thermodynamics. So this introductory thermodynamics will lay the foundation for phase coexistence. You see, most materials have more than one component in them. As a result, there is a tendency to form more than one phases which are in equilibrium with each other, and we will first look at the thermodynamic basis of how these phases can coexist with each other. So we will do introductory thermodynamics. This will take roughly 2 weeks of about 10 lectures. Okay, and then we will move on to equilibrium in multi-component systems. We will explain this in the context of what we call as phase rule. Okay, so this will be done in about a week, 1 week, which will be about 5 lectures. So basically these two topics put together will be about 15 lectures, and they will constitute what we call as thermodynamic basis. Of phase equilibrium. Then we will talk about, once we have understood how phases coexist with each other, what are the free energy arguments as a function of temperature and composition, we will move on to defining a concept called as phase diagrams. Okay, and in this phase diagrams, we will look at phase diagrams. What is a phase diagram? So we will look at the definitions. Then we will look at single component systems. We will look at binary phase diagrams, binary alloys / systems, and then we will also introduce ternary. We will not get into details of ternary, but ternary systems. These three put together will take about I would say nearly 15 lectures or about 3 weeks, and then we will move on to some examples, and examples will consist of iron carbon phase diagram. The most calibrated phase diagram and other common alloy systems, followed by so this will take about again 5 lectures or so, and finally we will come to what we call as phase diagrams vis-a-vis microstructures. So this will again take about 5 lectures. So in total, if I go back to previous slides, so in total we have thermodynamic basis will take about 15 lectures, then phase diagrams, various definitions, various reactions and phase diagrams corresponding to single component binary and ternary systems will take about 15 lectures. Then finally, some example phase diagrams and phase diagrams vis-a-vis their microstructure of materials will take about roughly 10 lectures. So 15 plus 15, 30 plus 10, we will have about 40 lectures, so which is the mandate of this course. So let us begin with the basic thermodynamics of materials. So we will begin with essential So first I would write the reference that you must read. So reference is chapter 1 of phase transformations in metals and alloys, and it is authored by Porter and Easterling. This is basically a Wiley Publications book. So this chapter is very useful as far as understanding the concepts of phase formation or phase equilibria is concerned. So within this thermodynamics, we will first begin with what do we mean by equilibrium, then we will look at basic thermodynamic relations, then we will look at single component systems, single component systems, and then binary solutions, and then we will look at heterogeneous systems. The focus will be on understanding how the free energy changes as a function of thermodynamic parameters, which can help us explain the phase coexistence. So let us first define a few thermodynamic parameters, such as so we will just look at first definitions. Okay, and the definitions we will first start with what we call as systems. So let's So in thermodynamics, we generally call a material or an alloy or a compound as a system. In the context of materials, a system is defined as basically an alloy or a compound consisting of one or more phases. Okay. So the alloy could be a one element alloy. So basically we can say a metal. So, alloy is generally a mixture of elements. A metal or an alloy or a compound consisting of one or more phases. So, it could be pure metal, it could be an alloy consisting of more than one element, or a compound, you can say, or more, consisting of more than one of phases. Now, the question is, what is phase? So, let us now define the phase. Now, a phase is defined as part of the system in which the properties, the physical and chemical properties are homogeneous. So, we can say part of a system with homogeneous chemical and physical characteristics. Okay. So, for example, if I take as an example if I take the example of water, H2O is a molecule, right? It does not normally dissociate under usual circumstances. H2O can be present as vapor, water vapor. It can be present as water, which is liquid. This is a gas, and it could be present as ice, which is a solid. Okay. Now, these are three different forms of water, H2O molecule, present in solid, liquid and gaseous forms, and although the chemical composition of ice and water are the same, but their physical characteristics are different. So, they do not have identical physical characteristics as well as other chemical parameters, thermodynamic parameters. So, that is why water and so these are, you can say, three different phases of water, okay, or three different phases of H2O, three different phases of H2O. Similarly, let us say, so you have, when you have let us say you have a mixture in which you have ice and then you have, so these are solid ice particles. So, this is water and this is ice. So, although the chemical composition of these is similar, this is also H2O, this is also H2O, but they are physically distinct from each other. As a result, they are two different phases. So, although chemical formula is same for both of them, but their physical characteristics are different, even the thermodynamic parameters are different. As a result, these are two different phases, and when they coexist with each other, it is coexistence of the two phases. Okay. So, these are, so similarly you can have, for example, salt and water. Okay. So, let us say you have a solution. So, and in between you have salt crystals. Okay. So, this is, so here what we have this is NaCl crystal, and the other thing that you have is basically the salt solution. Now, salt solution is the solution in which salt molecules are homogeneously dispersed in H2O phase. So, it is distinguished, it is not possible to distinguish between what is, whether one region has more sodium, one region, so it is pretty much homogeneous mixture of salt and solution. So, this is one phase, this is called as phase 1, which is distinct from pure water. Okay. So, this is phase 1 and this could be phase 2, it is a solid phase, chemically and physically distinct the salt solution. Whereas salt solution is distinct from water, it contains mixture of H2O molecules and NaCl molecules in the liquid phase or the liquid form. So this is phase 1 and phase 2. They can also coexist together. For example, you have supersaturated solution of salt in water, that will make two phases coexist with each other, the liquid salt solution and so this is liquid and the solid NaCl crystals. So these are two examples in case of simple systems. In case of for example, those who know metallurgy, steel for instance at room temperature consists of, so steel is an alloy of iron and carbon, so let us say 0.2% carbon. Okay. So it is an alloy of carbon, it consists of a phase called as ferrite and another phase called as cementite. So ferrite is iron with very small percentage of carbon, 0.008% of carbon, and cementite is a compound called as Fe3C. These two phases are present in steel. So if you look at steel under the microscope, you will see, I will just zoom a region. So you will see for example a colony. So you will see a colony in which these are your plates. So this could be cementite and this could be, now they are both solid phases, but chemically they are distinct and physically also they are distinct, they have different physical characteristics. So this is phase 1 and this is phase 2. So these are some examples of what do we mean by phase. A phase is something, a region of the crystal in which a homogeneous region of the crystal which has different physical or chemical or both kind of characteristics as compared to other regions of the system. Now let us look at the third definition. The third definition is called as, now phase consists of, each phase consists of elements. So third thing is called as components. So for example, we saw in case of steel, so we have steel is an alloy of iron and carbon. So it has two components, iron and carbon. Okay, component 1, component 2. Similarly, if you look at water, water consists of H2O, which is a bound molecule. So this is the component in water, this H2O. So it is one component. So in this case, you have two components whose distribution make up phase 1 and phase 2. In this case, you have only one component, that is H2O. H2O does not break. So it is the same H2O molecule which is present in different conformations in water, in gas and solid phase. So similarly, if you look at brine solution, brine is nothing but H2O in liquid phase plus NaCl, which is dispersed. So this is component 1 and this is component 2. So within the solid solution, within the solubility limit of NaCl in brine, the NaCl is dissolved in H2O phase, in liquid H2O phase completely, but it is present distinctly as second component. So these two components are miscible into each other in brine, but when it is supersaturated solid solution, so when the supersaturation happens, then you have brine plus NaCl, two different phases. This phase consists of only NaCl, this phase consists of NaCl plus H2O. So it is a system with two components, NaCl as one component and H2O as another component. It is just that NaCl still, although it is a compound consisting of sodium and chlorine, it is a bound phase. So we take the compound as a component where the compound does not have tendency to break into sodium and chlorine separately. So these are called as components. So components are elements or compounds. Compounds could be in the bond form constituting the phases within a system. So basically you can say the hierarchy is you have a system which is an alloy or compound in most cases. System consists of phases, okay. So, you can have one or more. Each phase consists of elements or compounds, so it has what we call as components. So, components could be either elements or bound molecules. So, for instance, it could be you can have one or more in a particular phase. Three thermodynamic definitions that we follow: system, phases and compounds, and this is the hierarchy in which they are arranged with respect to each other. So, basically you can say components are nothing but ingredients which are present in a given phase under certain set of thermodynamic conditions, mostly temperature, pressure and composition. Now, these phases, so in this course we are worried about how these phases exist at equilibrium. So, basically so phase equilibrium means implies essentially how these present how in a system under a given set of conditions which are typically temperature, pressure and composition as far as material science is concerned. And in case of material science, generally pressure is taken as constants. So, we normally worry about temperature and composition. And then what is the distribution of these phases? And then what makes them what makes more than one phase coexist? So, these are the questions that we would want to answer as we go along. So, now when you have, now why is it important? It is important in processes of phase transformations, because when we process materials, material goes from one phase to another. So, there is a concept called as phase transformation. Okay. So, phase transformation is basically you can have phase 1 transforming to phase 2, for example. Let us say you can have H2O in liquid form transforming to H2O in vapor form, and this is when you increase the temperature. As you increase the temperature at the evaporation temperature of liquid, the liquid will transform into the gaseous form. This is transformation of so we can study under what conditions, thermodynamic conditions, the liquid phase is stable, and under what conditions the gaseous phase is stable. Similarly, what will happen if you keep the temperature constant but you change the pressure? At what pressure liquid H2O will transform into the gaseous H2O or solid H2O, for instance. So you can have phase 1 transforming to phase 2, you can have transformation of phase 1 to phase 2 and phase 3, and so on and so forth. So let us say this is P1 transforming to P2 and P3. So you can have variety of possibilities. You can have another possibility could be P1 plus P2, two phases are present, and under some transformation condition. So you can have some condition of temperature and pressure as well as composition. Similarly, here you can have certain condition of temperature, pressure and composition. They can give rise to phase 3 and so on and so forth. So we will see, so understanding of phase equilibria will make you understand how these transformations happen. And this is because when you change, for example, when you change phase 1 to phase 2, the transformation happens. So for example, you go from H2O liquid to H2O gas as the temperature increases. This is because at high temperature the H2O in gas form is thermodynamically more stable as compared to H2O in liquid form. Or in the thermodynamic sense, we say the free energy of H2O in gas form is lower than free energy of H2O in liquid form at high temperature, that is temperature in more than 100 degrees centigrade. So we look at the reasons behind this. So when we understand phase equilibria, we will be able to explain these things in a better fashion. So we'll finish this part here. In the next part, we will again move on to building this thermodynamic basis further. Thank you.